Hello, I am Paul Dietz, a technical fellow at Tactual Labs, and today I'm going to be talking to you about shape sensing and the future of shape. Today, we're going to start by looking a little bit at the history of shape and how the shape of everyday objects has changed over time and the forces that have caused that to be. Then we're going to take a look at different types of shape sensors, or bend sensors in particular, that we use to measure shape and in particular changing shape. And those have various issues that will motivate our own work on shape sensors that I'll discuss next. And in particular, we'll be talking about ShArc sensors and explaining what those are and what properties they have and why they're so interesting. Then we'll move on to applications of shape sensing, and I think you might find some surprising ones in there. And finally, we'll talk a little bit about the future of shape itself and how that will impact our future lives. Let's start with a simple example. Let's say I gave you this vase and asked you to measure its shape very precisely so that somebody remotely could look at your measurements and reproduce it exactly. That's actually a pretty hard task if you're using traditional tools. For example, tape measures and calipers are really good at measuring linear distances, but they're not good at measuring curvature. So back in the days when things were mostly handmade, shape was something that was not very well defined. So if you take a look at this cuckoo clock from around 1900, you can see there's a lot of detailed, delicate carving on it. And if you had a fine craftsman trying to reproduce this, they could get something that looked quite like this, but would be probably significantly different in details. This clock would be extremely hard for someone using those traditional tools to be able to, measure it precisely in a way that someone could reproduce it just from those measurements. There's no mathematical precision for measuring something like this using those tools. Now, when we move to an era of mass manufacturing, there were some opportunities to build shapes using those kind of traditional handcrafted techniques. And particularly molding lended itself really well to this. So if you take this example of the original Coke bottle, this is something that they could have handcrafted very carefully, gotten it as nice as they wanted, produced a mold from it, and then from that mold produced millions of Coke bottles. In that process, you never actually had to define the shape mathematically or with any deep precision. The mold itself was the example, but it was never produced in a documented way. Well, as time wore on, clearly there were engineered objects that needed to be done with precision so others could reproduce them. So if you look, for example, at electronics in the 1930s, you could see that they tended to have very geometric designs that were very easy to describe. So this particular object here is actually the first commercial FM radio. I have a connection to this because the case for this was actually designed by my dad in 1938. And you can see that the design here, very simple rectangular things that are very easy to measure using simple tools. And the circles, again, also very simple geometric constructs, very easy to measure and describe. By the 1970s, CAD, or computer-aided design, had started to emerge, and we could design far more complex objects using these computerized systems. But those early systems really didn't have good tools for describing shape. And so a lot of the objects that were designed in that era were really combinations of very simple geometric forms. And you can see that in this example of what personally I consider the ugliest car ever made, the Chrysler K cars, that they had these very boxy designs. And to some degree, that was a result of the CAD tools that were used to describe them. It's often said in design that form follows function. But it's equally true that form follows tools. The sorts of tools that we have available to us very strongly influence the sorts of designs that we make. So if we have tools that make it easy to do simple geometric forms, that's what we tend to design. And that influences even our imagination about what sort of shapes are possible. I think the best example of this is if you look at the spacecraft of science fiction from the 1970s, they tend to be collections of simple geometric shapes. The Death Star from Star Wars being a simple sphere is a great example of this sort of thing. After decades of drawing tool evolution, we got to the point where we could describe complex curves fairly straightforwardly in our tools. And then you started to see in science fiction that the spaceships that we imagined were very curvy and had very organic shapes. Form follows tools. So what we've talked about up to this point is static shape. But things get much more interesting when you allow them to evolve and change in dynamic ways. So it turns out that the tools that we have right now are actually very good for describing complex curves, but they're not very good at describing the evolution of complex curves. And in fact, just the way that we design things that moves tends to be much simpler than, for example, the way that this octopus moves. If you take a look, almost every object that we design to move uses a combination of simple rotary and or linear joints. That's kind of the tools that we have available to us. We don't think in terms of these complex deformations because we don't have the tools to do that. Now, interestingly, you might think, oh, well, maybe we don't have the actuators that can do these sorts of detail motions. But in fact, there's been a lot of work in soft robotics to do arrays of actuators that can create very different sorts of deformations in very complex ways. But what's really missing there is the ability to control them. They tend to be open loop. And so what we really need are sensing systems that can tell us what shape we currently have and drive it in a feedback loop to a very particular shape. That's what's missing. It turns out that human motion is also very complex. You might think, oh, well, we just have a bunch of simple joints. But in fact, those joints move around in very complex ways. And there's a lot that you can do with them and the surrounding muscle and tendons that's very non-obvious. We need to understand human motion for a lot of different applications. So for example, if we want to put people in virtual reality spaces, we need to be able to have an understanding of pose in real time. And unfortunately, that's still a poorly understood problem. There are other places where this need comes up. For example, in understanding how athletes perform, it's often necessary to use sensors to understand their particular pose and how that evolves. Another place is in medicine, when you're trying to get an understanding, for example, in rehabilitation therapy, how about joint movement is evolving as the therapy progresses. These things all need ways of sensing complex human motion. Well, the way we try to solve this problem now is with these resistive bend sensors. That's the most common solution. And resistive bend sensors are very inexpensive, which is fantastic. They've been around for well over 20 years, but they have a lot of drawbacks and limitations. So the way these things work, they're basically a strip of plastic that carbon has been deposited. And so when you bend that strip, the carbon is actually strained and pulls apart if you bend it one way, or compresses the other. And that changes the resistance across the strip. And so what you measure with this sensor is the resistance, which is a function of the flex it's undergoing. Now, you only get at one number, right? Because it's just the resistance. So it's really a very rough measure of flexure. It doesn't give you any sort of detailed curve. It also is not a very stable device because you're measuring this material. That material is fairly temperature sensitive. It changes with humidity. It suffers from fatigue. If you work it a few times, you get a different answer. So they're not very precise devices, but they've been used extensively to take a look at how humans are moving. And probably the best example of this, an early one, was the Nintendo Power Glove from the 1990s. This had resistive bend sensors in each of the fingers to try and get some idea of how the finger was moving, but it was a very crude measurement at best. So, as I said, the problem with simple bend sensors is they only give you a single measurement of flexure, and that doesn't really reveal the shape of a complex curve. So there have been more modern attempts to make better versions of these sensors that don't suffer from drift. For example, there are companies that make capacitive versions, but they still have this problem that they just give you one number out to describe flexure. So this picture that I have here was actually taken from the literature from one of these companies, and it shows that each of these shapes actually produces the same measurement. So these to the sensor are all identical shapes. Now, I think that's a significant bug because if you have a shape that's complex, you can't just use one of these sensors to tell what's going on. So traditional bend sensors are really restricted to cases where you have a single bend. But if you want to measure a complex curve with many bends, you might think, aha, I'll just use a bunch of these bend sensors connected in series so that I can measure all those complex curves. That turns out to be problematic for a very simple reason. The angular error that you measure at each joint accumulates so that by the time you get to the end, your understanding of the angle is the sum of all the measurement errors along the way. It's this box that you're in. The more encoders you add to get a good understanding of the curve, the more the measurement error increases. That's why these systems are fundamentally not a good choice for measuring complex curves. So now we get to the really exciting part. And that's the sensors that I've been working on, which are true multi-bend shape sensors. And we call these ShArc for shift arc. And this video explains the basic idea.
ShArc is a precision geometric measurement technique for creating multi-bend shape sensors. These devices are designed to detect curvature in the XY plane. Most bend sensors report only a single number, which is a gross measurement of overall flexure. In contrast, ShArc sensors can provide detailed shape, even when there is more than one bend along the sensor. ShArc sensors detect curvature at many points, building a model of the shape from a series of connected circular arcs. This particular prototype creates models using 8 arc segments, but the technique easily scales to using many more arcs. ShArc sensors are extremely low cost, highly responsive, precision measurement instruments. Most bend sensors detect bending by measuring strain in some material. In contrast, ShArc sensors directly measure changes in geometry and are more like digital calipers. Here, we show the accuracy of our prototype sensor. The graph shows both the live data from the device as well as the known geometry of a 3D printed form. When we shape the sensor onto the form, you can see how well the measured data corresponds. Even the unintentional small gap at the end is well modeled. ShArc sensors are built using 2 flexible strips that are held a constant distance apart. In our prototype, there are transmit and receive strips that each contain a series of carefully designed electrodes. The spacing between the transmit and receive strips is set by a series of spacer strips. A small clamp on one end binds the stack, and an elastic sleeve keeps the strips aligned and pressed together. A circuit board measures the capacitance between the electrodes on the transmit and receive strips. ShArc sensors work by measuring relative shift to fit arcs. Imagine 2 measuring tapes held a fixed distance apart and joined on one end. If this unit is held flat, the measurement marks on the 2 tapes will align. But if the unit is formed into a circular arc, the inner strip will have a smaller radius than the outer strip. Assuming the 0 points are constrained to a line, the other marks will drift apart. The tighter the curve, the more the 2 sets of markings will diverge. This is similar to what happens when a paper book is bent. The binding keeps one side of the pages aligned, but the other side fans out. Our prototype measures shift via changes in differential capacitance. The bottom strip contains a series of transmit electrodes. The top strip has corresponding pairs of receive electrodes. As the transmit electrode shifts relative to the receive pair, the circuit becomes unbalanced, creating larger capacitance to one side or the other. Measuring this differential capacitance reveals the degree of shift. Our prototype has 8 measurement pairs. When flat, all are aligned, giving 0 differential capacitance. But as the sensor is curved, the transmit and receive strips progressively misalign. By measuring the shift over each segment, we find its radius of curvature. Because the total shift to any measurement point is the sum of the shifts in all of the segments, the total curvature to any point can be found irrespective of any subsegments. This gives ShArc sensors a unique tolerance to measurement errors. Unlike jointed systems with encoders, angular errors do not accumulate with each measurement point. We prototyped a number of sample applications for our sensor. Our first demo uses the sensor to detect the shape of a bent finger, as might be used in a virtual reality glove. Because the shape is modeled by many arcs, there is no need to make presumptions about the location of finger joints, as is required with less capable sensors. Given the precision of the device, it is ideal for measuring complex curves on objects. Shapes of real objects can easily be entered into CAD or other drawing packages. We created a long version of our sensor to detect curvature of the spine. This is useful for providing real-time feedback and long-term monitoring of posture. This also suggests many applications in physical and rehabilitation therapy. Everywhere we look, we see things that bend. ShArc sensors provide a precise and cost-effective way of understanding the shape of our world.
Over the last year, we've been busy on making a commercialized version of the ShArc sensor that really is a second generation ShArc sensor, which we call bend shape. Here are some of the characteristics of this new version. Again, it's 160 millimeter sensing length, which is about the same as the first generation. But instead of 8 segments, it has 16 segments. The read time is 6.5 milliseconds. So this means this sensor runs at over 150 hertz. So it's quite responsive, quite fast. Another key change is that the sensing bend limit on the original prototype was limited to a maximum of about 180 degrees anywhere over the sensor. Well, on this device, the limit, because of a new encoder design, is actually per segment. So the limit here is about plus minus 90 degrees per segment. And in fact, you can coil this thing up into a spiral and actually have that work. So it's a much greater range of motion that this sensor can sense. Really, the limit on that is the mechanics. So if you want to keep it accurate, you probably don't want to go much beyond a full circle. But for most applications, that's certainly sufficient. And we've also been life testing these devices, and we are seeing lifetimes in excess of 2 million flexures. Basically, we stopped testing after that. So these devices are looking very promising. Next, we're going to take a look at some of the applications for bend sensors. There are quite a few, and we're just going to touch on a handful, just a tip of the iceberg. Let's consider the use of shape sensors as expressive input devices. Now, shape sensors are kind of like knobs and sliders in that they're physical devices, and you can feel physically where you're manipulating them to. But they're quite different from those devices because they have many degrees of freedom. Your typical knob or slider is only 1 degree of freedom, but these devices are actually putting out lots of data, and that makes them very expressive. And that's good for a lot of applications where you want to dynamically control some expressive thing. And typically those applications require a fast response, so it's a good thing that ShArc sensors are fast. So I want to give you a little example of this. We've been working with the University of British Columbia, and we have a paper that we'll be presenting at the New Interfaces for Musical Expression conference later this year. But I want to just show you a little bit about the power of using a shape sensor as an expressive musical device.
For the guitar effect, I created a vocal synthesis engine, which we'll call the VOC plugin here, using Paul Batchelor's VOC library, which is based off of Pink Trombone. This model of the vocal track treats it as a series of 44 cylinders whose diameters filter an excitation signal to create human voice sounds. To control using bend shape, we partition the sensor into 40 segments and use a Y position value of each of these segments to control the tongue shape of our tracked model. To use this as an effect, we can use any instrument as an excitation signal and shape it using the VOC plugin. This next clip demonstrates how it sounds when used on an electric guitar.
Shape sensors are going to revolutionize the way that we build robots. That's a pretty strong statement, but let me explain why. The typical industrial robot arm right now weighs about 10 to 20 times as much as their maximum payload. Now, Obviously, that's not true for us. We can lift things easily that are close to the weight of our arm. So why are these mechanical devices so limited? Well, the answer is pretty straightforward. It's because they count on joint encoders to accurately know the position of the arm. For that to work, you've got to make sure that the arms do not flex, because otherwise the measurement would be off. And so these arms are typically way overbuilt, not to just hold the weight, but to hold it without flexing at all. And that's hard, and it's what makes robots very heavy. And it's not just robots, there's all sorts of mechanical devices that have this problem. So imagine now instead that you had a device that let you understand in real time exactly how the mechanism is bending. Well, then you can put that into your feedback loop, and it's okay if the thing bends. So in fact, you could build much lighter mechanisms for robots and similar sorts of devices. This is going to be a super important application of bend shape sensors. In our robot arm example, flexure was an undesired thing that we were creating an ability to work around. But what if flexure was actually something that you were using as a design element, that you specifically wanted things to flex, and that was a critical part of their operation? So this field is known as the design of compliant mechanisms. And so, for example, we've been talking with our friends at Brigham Young University, Larry Howell's group, that has been working on compliant mechanisms for quite some time. And these are a really intriguing thing because it gets around this problem I talked about earlier of most things that are designed to move are designed to do it using either simple rotary or linear joints. But when you design things to flex, there's a lot of advantages to that rather than making traditional joints. The thing to keep in mind is that the problem with doing compliant mechanisms traditionally has been there's no good way to get feedback for their state. Well, shape sensors let you do that. So let me just give you an example from Larry Howell on the power of compliant mechanisms.
It's always been considered to be bad to have flexibility in your machines. Well, we've tried to take that thing that everybody hates that is trying to avoid and say, how can we use flexibility to our advantage? How can we use that to do cool stuff? Probably the first compliant mechanism I ever designed was this thing. What it is a compliant mechanism that is a gripper. So you can put something in there and it'll get actually a really high force. I can put that in there and it breaks the chalk. So that looks like a crazy beast, but every part in there has a purpose. All these flexible beams, here are the two inputs. And again, we did this with NASA for a thruster application where you can put a thruster right there. And now with our two motor inputs, we can direct that thruster in any direction. That titanium device moves that. And you notice that it's just all bending. And then there's no pinch points for the fuel lines or electrical lines coming in.
Another really interesting application of bend sensors is in structural health monitoring. So we've already discussed that ShArc sensors don't need recalibration, that they can work for decades without the need to recalibrate them. That makes them ideal for monitoring structures like bridges and buildings to see if they're deforming. And so that's a really great application. But in some ways, that's not using the full capability of the sensor because ShArc sensors are also fast. So you can actually monitor real-time fatigue. So for example, if you consider something like an airplane wing, as the plane flies, the wing is bouncing around all the time. And all that accumulated stress is potentially fatiguing the metal over time. Well, if we can monitor that fast enough, we can actually create basically a gas gauge for materials to know when they're reaching their fatigue limits so that we know when we will need to replace things based on not just how much time they're up in the air, but the actual stresses and forces that were applied to them in operation. These sorts of bend sensors are also great for understanding human dynamics. And I probably don't have to tell anyone here that pose tracking for AR and VR is an important application and something that finally you can do with precision without having to have a device that's offset and looking at somebody, but can actually just be built into their clothing so that you can know with precision what they're doing. Of course, that same technology has lots of applications in things like rehabilitation therapy. So one of the things that we've realized talking to customers for our bend-shaped devices is that there's a huge market for doing clothing that can monitor humans, just like we do structural monitoring, that we can do monitoring of humans to know in the workplace. Are you stressing your back? How much accumulated fatigue do you suffer in the day walking back and forth through the warehouse? These are the sorts of things that we can know in detail. And so we know that shape sensors are going to become a very important tool for understanding human performance in those sorts of situations. Another interesting thing is that because we have such detailed data on shape, we can use this for all sorts of super interesting medical sorts of monitoring applications. So for example, if you can put these sensors, encase the body in them, you can understand in detail three-dimensional shape in motion. So you can understand dynamically how is blood pooling in the body, what is happening with the lungs as you breathe, what's happening with the position of a fetus, and all sorts of subtle shape changes can be monitored in detail very inexpensively. Well, those are just some of many applications for shape sensing, but I want to take a few moments now just to look forward and think a little bit more generically about the future of shape. So as we speak, there are actually many technologies in development that allow very detailed actuation. So for example, in the soft robotics community, you see a lot of work around artificial muscles using pneumatics, electroactive polymer actuators, shape memory actuators. And the thing that's nice about these things is that you can have lots of them. You can have very dense arrays, and you can do really interesting stuff in terms of creating complex motion. But the problem for all of these has been that you don't have good feedback mechanisms, that these systems tend to work open loop right now. And precision measurement is the key to precision actuation. So once you have the ability to sense this stuff, you have the ability to move it precisely. And so clearly the sorts of sensors that we've been looking at are going to be paired with detailed sorts of actuators to create true programmable shape. You know, I love the work that's been done by Hiroshi Ishii's group at the MIT Media Lab to give us a little glimpse of what this might be like when surfaces can just be programmed. Well, of course, you know, this is very intriguing, but the mechanism just seemed crazy, right? There's all this hardware, it draws a ton of power, it's very expensive. But in the future, you're going to be able to do these things with simple strip devices that provide actuation and sensing just in that strip form factor. So when I think about programmable matter of the future, I kind of think of it in stages, kind of a hierarchy. So at the very bottom, there's this ability to program shape that will have these simple strip actuators that you'll be able to command with precision to go to a particular shape and hold that. But it gets more interesting once you say, I can do that, but I can keep changing it all the time. I can dynamically program the shape, so I can have movement and I can control how that happens, how the shape evolves over time. The next level beyond that is when you integrate sensing with those strips. And in fact, there's lots of sensing modalities that integrate into that strip form factor very easily. So for example, sensing pressure or proximity or temperature is pretty straightforward. So once you have those sorts of sensing capabilities built into your programmable matter, that means the shape can react to it in real time in interesting ways. So for example, you'll be able to program behavior at a very detailed mechanical level. So if you want a section of the strip to feel springy, you can do that by basically programming in an F equals minus KX sort of behavior. Or if you want it to click like a switch, you can program in that sort of nonlinearity. So that's what you can do once you have those sorts of simple sensors in there. Then finally, if you want to get to Terminator level sort of programmability and talk of science fiction dreams of the future, the key is adding more output capability, and specifically adding flexible displays on top of that. And we've seen there's been tremendous progress in the last few years in making flexible displays that could in fact be integrated on top of all of this. And so once you have that, then you have a material that, a programmable matter material that you can program the shape of it, you can program its behavior, and you can program what it looks like. And that to me is the future of programmable matter. I just want to take a moment at the end here to thank my collaborators in this work, specifically all of the many people at Tactual Labs who have contributed to this project, as well as some of the people at universities that we've worked with at the University of British Columbia and at Georgia Tech in particular. Thank you very much. And if you have questions, I believe there's a Q&A session coming up, but you can feel free to reach out to me at paul.dietz@tactuallabs.com. Thank you very much.